So what I'd like to do today is an example problem on sedimentation. As I understand it, the design project in 495 is a wastewater treatment plant design. And it's focused on redesigning wastewater treatment so that one can recover nutrients and energy. So a number of you are also in 495, so I decided to focus this problem on wastewater rather than water treatment. We'll talk about wastewater treatment later, but what I'd first like to do is just a little review of wastewater treatment. You may remember this from 280, perhaps not, but let's just look at wastewater treatment. So we have wastewater that comes in from the sewers, collected from homes, industry, etc. Typically, that will go through some sort of preliminary treatment. This includes bar screens, comminutors, grinders, operations that are used to take larger material and grind them or into smaller particles that won't harm the pumps, won't clog piping, or to actually remove that material. From there, it goes into a grit chamber. Now, a grit chamber is designed for type 1 sedimentation. That is the removal of discrete particles. Grit chambers remove what is referred to as grit. This is just fairly coarse material, about the consistency of sand, coffee grinds, could be eggshells, material that will just settle without coagulating, so it won't interact with other particles. Typically, you're looking at removing particles somewhere from about 100 microns up to about 300 microns. So can think of that as fine sand up to more coarse sand. Typically, this is fairly inorganic. We're looking actually to keep the organic material in suspension in a grit chamber, but to remove the inorganic material. From there, the effluent from the grit chamber goes into primary sedimentation. So we have the grit, and that is typically landfilled. And then the effluent from that flows into primary sedimentation basin. These are the sedimentation basins from the East Lansing wastewater treatment plant. Same type of apparatus that we've talked about in terms of the launders. You can see the launders right in here. So the water flows over the weir, and there's actually a weir here, and then into a launder, and then into a central collection channel. Your wastewater sedimentation basins typically also have scum collection because there is material that floats, that will float to the surface, and that material then is collected into what is known as a scum trough, which is what you see here, and that then can be further treated or can be landfilled. From there, the effluent flows into an aeration basin. The sludge from the bottom is then typically further processed through some sort of sludge thickening. Dewatering may require subsequent treatment, for example, stabilization. Basically, what we're looking at doing is trying to make sure that that sludge doesn't negatively impact the environment when it's ultimately discharged. Some cases, stabilization can be digestion, where you're looking at, again, reacting. You're using microorganisms to react that organic matter, consume that organic matter, and typically you're looking at producing CO2 and methane. We're looking at stabilization. Stabilization can also be incineration, where we're not obtaining any useful energy from the material. Now with aeration basins, we're again using microorganisms. What we will do is we'll add oxygen. We also then take the sludge, some portion of the sludge from the secondary clarifiers. This is our referred to as return activated sludge, that contains all these microorganisms that are useful for degrading that organic matter. So we're taking complex organic matter and we're converting that to CO2, nitrate, or if we have denitrification, nitrogen, phosphate, which we may precipitate as often ferric phosphate, so that when this material is released to the atmosphere, when this water is released to the atmosphere, to a receiving body of water, it doesn't consume oxygen, or doesn't consume so much oxygen that the body of water goes anaerobic. And then we have waste activated sludge, and that would go through further treatment. So the effluent from the aeration basin flows into a secondary clarifier. This is the second on the right, sorry, in the left is the secondary clarifier from the East Lansing wastewater treatment plant. On the right is the wastewater treatment plant. Sorry, the secondary clarifier from the Williamston wastewater treatment plant. The difference in color really just has to do more with happens to be the day that was taken. Happened to be a sunny day versus a really cloudy day. So it's really not indicative of treatment. And then the effluent from that secondary clarifier is often further treated. So I'm just going to put tertiary treatment, which we will talk about later in the semester. And then it gets discharged to a lake, river, etc. So just to give you a sense of overview of wastewater treatment, especially for those of you that may be in 495 right now. Any questions about any of this? Skipped a few slides here. These are just images of sludge thickening tanks. Same type of system that we've talked about before. Here, the example we used before, it was a chain and flight system. This is just a rotating arm that is pushing the sludge into a hopper. And you can see here the launders, and then there would be a main channel in the center to collect the effluent. And there's just some images to show you some wastewater. The first image on your left is about the consistency of what we call the mixed liquor from an activated sludge tank, and then you can see it's settling. Okay, just going back here in terms of, I mentioned type 1 settling with a grit chamber. With primary sedimentation, that is typically type 2 settling, where we start to have aggregation of particles. They can collide and then they settle more rapidly and more efficiently. We may or may not be adding coagulants. in a primary sedimentation basin. That coagulation may actually be essentially naturally occurring. We have type 3 or hindered settling. In a secondary clarifier, we've got a more dense sludge. So our mixed liquor has a much higher suspended solids concentration than our effluent from the grit chamber. So we get much more aggregation, much more interaction of particles. And then we can have type 4, which is compression settling, where the weight of the sludge in the upper region actually compresses and pushes out the water in the sludge at greater depth. So you actually get dewatering in the tank itself. Work through the problem solving a design of a horizontal flow gravity grit chamber. We're looking at designing this to remove spherical particles. Why spherical? Because then we can use Stokes' law. They have a diameter of 1.71 times 10 to the minus 4 meters. So it's about 171 microns. The depth of the grit chamber is 1 meter. You're told that the detention time of the liquid in the grit chamber is 60 seconds. The particle density is 1,830 kilograms per meter cubed, and the temperature of the water is 12 degrees. So the first thing that I'm asking you to do is to determine the overflow rate and then estimate the terminal settling velocity. Why do I say estimate? Is there any piece of information that at this point we don't know? We don't know whether we have laminar flow. We haven't measured, we determined the Reynolds number, and Stokes' law depends on the Reynolds number. So the overflow rate is defined as the flow rate divided by the surface area. So it's the flow rate divided by the length times the width, and that is equal to the height or the depth of the basin divided by the detention time. And I go through derivation of this in the slides that I've provided. So the height is 1.0 meters. We're told that the liquid detention time is 60 seconds. It's different than the solid detention time. But for the overflow rate, we're looking at the liquid flow, and that is equal to 0.0167 meters per second. Okay. Now, the challenge with determining the settling velocities, as I mentioned, we need Reynolds number in order to determine which equation to use. We don't have that a priori. So what we need to do is we'll estimate the terminal settling velocity using this equation. It's just Stokes' law. So gravitational acceleration times the difference between the particle density and the fluid density times the diameter of the particle squared divided by 18 times the dynamic viscosity. This is the same approach we will also use in filtration for head loss calculations. So the same sort of iterative approach. So substituting, we have 9.1 meters per second squared times 1830 minus 999.5, that's kilograms per meter cubed, times the diameter of the particle. Make sure this is in meters, 1.71 times 10 to the minus 4 meters square that, divided by 18 times the dynamic viscosity at 12 degrees C, which is 1.235 times 10 to the minus 3 Pascal seconds. And that gives us 0.0107 meters per second. Okay, so that is our first estimate of the terminal settling velocity. The next thing we need to do is to determine the Reynolds number. Okay. From that, we need to assess whether or not Stokes' law is valid, and then determine a better estimate of the terminal settling velocity. So the first thing we need to do is to determine the Reynolds numbers for the particles, as you've noted. The Reynolds number is equal to the diameter of the particle times the settling velocity of the particles divided by the kinematic viscosity. So notice this is a Reynolds number for the particles. So it's for the settling of the particles. So the diameter of the particle is 1.7 times 10 to the minus 4 meters. The terminal settling velocity is what we just calculated. The kinematic viscosity is 2.36 times 10 to the minus 6 meters squared per second. Apologize for the lines. And that is equal to 1.48. So that is greater than 0.5. So we need to obtain a better estimate. So the answer is no, it's not for the equation that we just used. So now we've noted that what we have is we have transitional flow, which means we need to use the more complicated and more general form of Stokes' law. First thing we need to do is calculate the coefficient of drag, as you've noted. So that is 24 divided by 1.48 plus 3 divided by the square root of 1.48 plus 0.34. And that is equal to 19.01. We then calculate the terminal settling velocity using the more general equation. So we can use the equation that the terminal settling velocity is equal to, it's the first equation on your equation on your notes, 4 times g, 9.81 meters per second squared, times the difference in our particle density and our fluid density, times the diameter of the particle divided by 3 times the coefficient of drag times the density of the fluid. And this equation applies, and I've noticed I've said fluid. This equation applies whether you're looking at settling of particles in water or settling of particles in the air. So for instance, you could look at it for settling aerosol particles in a classroom. So we have terminal settling velocity, we calculate that, and that is 0.00989 meters per second. Now, that is still an estimate, okay? In order to obtain a more accurate estimate, then what you need to do is you need to iterate on this solution. So note what we would do is, now that we have this terminal settling velocity, we would go back, we would calculate Reynolds number again. We would use the new Reynolds number to calculate a new coefficient of drag. We would use that coefficient of drag to calculate a new settling velocity, and we would continue to do that until the terminal settling velocity value actually converged on a solution. And if you do that, you find that the terminal settling velocity is 9.23 times 10 to the minus 3 meters per second. You can do that manually, or you can do that in Solver. So the next thing you need to do is determine the percentage of particles removed. Now, one of the things to think about, think of a grit chamber or a horizontal sedimentation basin as just a rectangular box cube. So particles come in here. Some of those particles will settle. So notice these particles will all settle. However, if that particle enters here, it won't settle. There isn't sufficient time for this particle to reach the bottom of the tank and settle. So we can calculate the percentage of particles removed in a horizontal sedimentation basin as simply, so this is the percent removed, as the ratio of the terminal settling velocity of that particle divided by the overflow rate. So we determined the terminal settling velocity of these particles. It's 9.23 times 10 to the minus 3 meters per second. And the overflow rate we calculated to be 1.67 times 10 to the minus 2 meters per second. We'll multiply this by 100, and that is 55.4%. So a little more than half of these particles would be removed in the sedimentation basin. That is true for horizontal sedimentation basins. For a upflow sedimentation basin, does anybody know the answer? Everybody watch the video. So we have an upflow sedimentation basin. So if this were an upflow sedimentation basin, it's not a great diagram, but basically what happens is the water flows in a center mixing. It flocculates in this interior cone in the inside, and then it flows up through this sludge blanket here, and then out over the weir on the top. So it's actually flowing. The liquid flow is up. The particles are moving down. So our particles are moving down. The liquid is flowing upward. So in that case, what for this type of a same size particle, would this particle be removed in this sedimentation basin? So what would be the percent removal here for the same size particle? The answer is 0. So in an upflow sedimentation basin, if the particle terminal settling velocity is less than the overflow rate, then no particles are removed. I then asked you to calculate if the grit chamber is 2 meters wide and 6 meters long, what is the maximum flow rate? And the problem with this here is we actually need a horizontal velocity. So let's calculate that first. Okay. So the horizontal velocity is Q divided by the cross-sectional area. So thinking about that same system, so we have flow in here. So we need to look at the cross-sectional velocity. It's the flow across this cross-sectional area. So we have a depth of 1 meter, a width of 3 meters. And I realized something with this is I actually calculated Q incorrectly. So the problem is I don't have a Q and I don't have which means I can't calculate a horizontal flow velocity. So I'm going to change this slightly, okay? And I'm going to give you a flow rate, and I'm just going to say that the flow rate is equal to 0.6 cubic meters per second. What I did in my calculations was I used the particle settling velocity, which doesn't make any sense. So we're just going to set Q as 0.6 cubic meters per second. The cross-sectional area is 1 meter by 3 meters. And that means that the horizontal fluid velocity is 0.2 meters per second. So I apologize. The mistake in my thought process when I wrote out the solution here. Okay, so I've just set the maximum daily flow, and then we can calculate the horizontal velocity. This same concept you're going to need in the homework. In the homework, if you have particles of different sizes, so here we have particles of one size. If you have particles of different sizes, different diameters, same density, and you're asked to calculate the overall percentage of particles removed, how would you do that? And you're given, so for the homework, there's a problem where you're given a mass percent of particles of different size. And you're given the density of the particles. And you're asked to calculate the overall percentage removal in a horizontal sedimentation basin. How would you do that? What you would need to do is you need to calculate the percentage removal for each particle size. And then you need to do a weighted removal and add up the weighted removals. So basically, here we had 100% of the particles that of 1.71 times 10 to the minus 4 meters. Okay, you had 50, so it's 100% times 55.9, so it's 55.9. But if we only had 50%, we would multiply by 0.5. We would have calculated the percentage of particles removed of this other size fraction, multiplied by that by 0.5, and add those two together. So think about that in the homework problem. There is one sedimentation homework problem that is very much like that.